Here's a very important way of constructing associative operations. We start from two functions, f1 and f2, each of which is associative. f1 is a binary operation on elements of type A1. f2 is a binary operation on the type A2. We will then define function f that operates on the pairs of elements from A1 and A2 and is also a binary operation. So it takes two arguments. The first one is a pair and the second one is a pair, and it returns a pair. How do we define it? In pretty much the only natural definition given the signatures of function f1, f2, and f. Given an argument x1, x2, and argument y1, y2, we will construct a pair consisting of two values, where the first value is computed by applying function f1 to x1 and y1, and the second one by applying f2 to values x2 and y2. Now we claim that f is also associative. Here's the rather straightforward but somewhat long derivation here. We start with the left-hand side of the associativity law. We see that f is nested in the appropriate way here. We can expand the definition of this inner f into application of f1 and f2. Now this means that the outside f applies to two arguments, each of which is written as a pair. So we can expand that definition. And now we have expressed f in terms of applications of f1 and f2. At this point, we can apply the fact that f1 and f2 are associative. We can therefore change the nesting of applications of f1 to the one on the right-hand side of associativity law and do the similar transformation for f2. We then simply apply the definition of f backwards. We recognize that what we have here is an application of f to the argument x1, x2, and this other argument, which in turn is application of f to the pair of y1, y2, and z1, z2. At the end, we obtain the shape on the right-hand side of the associativity law. So we have shown that f defined in this way is in fact associative whenever f1 and f2 are associative. Here's a simple application of the previous observation. Suppose we use 32-bit numbers to represent numerator and denominator of a rational number. We can then define multiplication that works on such pairs by simply multiplying the numerators and multiplying the denominators according to this function definition here. Now, because what we have done is applied multiplication to both components of the pair, and multiplication is associative even modulo 2 to the 32, the resulting function times is also associative. A prototypical example of applying reduce operation is computing the sum of elements in a collection. Suppose that we want to compute the average of elements in a collection. How could we do that? One way is to first compute sum by reducing the collection with the plus operation, and then compute length. If we do not have a separate way of computing length, one way to do that is to map the collection into a collection of constant elements, collection consisting of ones for every element of the original collection, and then simply compute the sum of such collection. The resulting collection will have as many ones as there were elements in the original collection. This will give us the length of the collection, so we can then divide sum with the length to obtain average. Now this computation invokes reduction twice. Is there a similar solution that uses a single reduction? Can you find it? The idea is to use associative operation on pairs. The first element of the pair computes sum of some subset of elements in the collection, and the second one computes the number of elements. It turns out we can combine both the sum and the length, the number of elements, using plus operation. Therefore, the resulting operation is associative. To get the effect of computing sum and length, we can then map the collection consisting of some elements by taking element x into a pair of that same element x and 1. So this 1 will be there in order to compute the length. Then we reduce the resulting expanded collection with function f that was defined before. So we'll be adding up all the elements x, we'll be adding up all the ones. What we will obtain at the end is a pair of the sum and the length of the collection, so we can again compute sum divided by length. We have emphasized that commutativity does not imply associativity. However, there are some cases when having commutativity can help us establish associativity, but we need some additional property. Let's define expression E of xyz to stand for the left-hand side of associativity law. We will say that the arguments of E can rotate if E of xyz is in fact equal to E of yzx. So conceptually, y moves to the first position, z moves to the second position, and x then goes to the last position. In other words, the condition we require is the following. Note that this condition has the same shape of application of f, but the names of variables are changing places. Now we claim that if f is commutative and the arguments of E rotate in this way, then f is in fact also associative. This turns out to be a very simple observation. If we start from the left-hand side of associativity law and then apply the fact that arguments can rotate, we obtain the following expression. Now we will just apply commutativity of f, which we have also assumed. So we can swap f of yz as the first argument and x as the second argument. And what have we obtained? We have obtained the right-hand side of the associativity law. So that means that these two properties in fact imply associativity. Even though the condition of rotation may seem difficult, it turns out to be easy to recognize visually in many examples. Let's define now addition on fractions, where their addition and multiplication is defined again modulo 2 to the 32. Given that we can have modular arithmetic and overflows in both numerator and denominator, which simply end up wrapping around modulo 2 to the 32, it may not be obvious whether such function plus is associative. Turns out the function is associative. We'll use the previous idea to show that. First, we'll observe that plus is commutative. Indeed, if we swap the roles of the one indexed variables and two indexed variables, we'll obtain, we can see that the second components are the same because of commutativity of multiplication, and that the first components are also the same. This is because of the commutativity of addition that we can also assume even with modular arithmetic. Now that we know that plus is commutative, we can try to show that the arguments of E rotate. So let us compute E as applied to pairs x1, y1, x2, y2, and x3, y3 by expanding the definition of E, which is always of the same shape given f, in this case plus. We obtain in several steps the following expression. Now, if we rotate the arguments, we can again apply what we have observed here just by substituting variables. So instead of ones, we write twos. Instead of twos, we write threes. Instead of threes, we write ones. And we continue like this. Because we have expanded here definition of E in general, it applies also to these other values that happen to be the rotated versions of the original ones. But now we claim that the result is in fact the same. We can see that The second components of the pair are the same because of properties of multiplication. What about the first component? Well, we have three parts of the addition, and it turns out that the first one corresponds to the third one in the new expression, second one corresponds to the first one in the new expression, and third one corresponds to the second one in the new expression. So now we have shown that rotating arguments of E gives in fact the same expression, and because plus is also commutative, we obtain that F is associative. Here's another example. Suppose that U and V are rational numbers in the open interval between -1 and 1. We can define F using the following expression. This is a nice symmetrical expression, and it is straightforward to verify that if U and V are in this interval, then the result is also in that interval. In fact, this is not an arbitrary expression. It corresponds to addition of velocities in special relativity theory when these velocities are in one dimension and normalized to the speed of light. Now it is easy to see that F defined in such way is commutative, because U and V play entirely symmetrical roles. Let us then compute the value of E with three arguments. So we have this nested application, then we combine it with W. After we bring everything to 1 plus UV, we obtain up U plus V plus W plus UVW, and below 1 plus UV from here, and then U times W plus V times W. Again, we see that we obtain an expression where every of the three variables plays the same role. In some sense, no variable is special. And because of that, if we swap the roles of some of these variables, we'll obtain exactly the same expression. In other words, the arguments of this expression E, the arguments of E do rotate. Because of the rotation and commutativity, we obtain that F is associative. This was arguably slightly easier than directly checking associativity law. Now it is tempting to implement such an operation using floating point numbers, and we can do that, but we have to keep in mind that floating point operations are not associative, so our calculations on the previous slide will not hold. And even though we could argue that the calculation will be only slightly off in one step, if we combine many operations F over a long collection, then these errors will accumulate, and we can obtain substantially different values for reduce versus, for example, reduce left on the same collection. This will not happen if, for example, we use rational numbers to represent these values. Let's now look at a family of operations that are defined using a closure operator. We'll look at operation F defined on sets such that F of AB is equal to A union B, to which we apply a closure operator. By a closure operator, we mean operator that creates a bigger set that is monotonic. So if A is subset of B, then A star is subset of B star, and that makes the set in some sense as big as it can, so that applying the closure operator twice is the same as applying it once. We'll call the last property idempotence. In practical application, we might not be computing with the sets of elements exactly, but we might be computing with their discrete representation. Examples of such operation and the corresponding closure operator is convex hull of a set of points or Kleene star for regular expressions. Now the claim here is that F defined in such way is always associative. Whenever define F in such way, and the three properties of the closure operator hold. Now we can immediately observe that F is commutative. F of AB is equal to F of BA because of the definition of F. Now if we look at the left-hand side of associativity law, we see that it expands to A union B star, and then union C, and then the whole thing star. And we claim that this is in fact equal to A union B union C and the whole thing star. Okay, so this is the main thing that we need to show. Because if we show that, then A, B, and C play entirely symmetrical role, So we'll have that the arguments rotate, and together with commutativity, we'll obtain associativity of F. To show the equality, we'll show two subset inclusions. Here's the first one. Now, obviously, if we have two elements in a union and we add third element, we'll get a bigger set. So that's a trivial property in naive set theory. Now we can use monotonicity of the closure operator and simply apply star to both sides of this equation. On the other hand, if we have set C, we can add A and B to it and we'll get a bigger set. And then if we apply closure to this union, we'll get something even bigger. This is one of the assumptions of the closure operator. What have we shown now? We have shown that both A union B star is included in this A union B union C everything star, and we have also shown that C is included in that same set. If you show that one set is included and another set is included in some bigger set, then the union of these two sets is also included in that bigger set. So we obtain the following conclusion. Now we can apply monotonicity. So we apply star to both sides of this subset inclusion. We have star here. We also get the star on the right hand side. But two stars collapse into one star. That's one of the properties of the closure operator. So we have in fact shown what we were aiming to show. And this is one side of the inclusion. Let's now show the other side. This is even easier. We want to show that A union B union C everything star is included into an expression where we have somehow additionally applied star to A union B. Intuitively, that should be even bigger set and everything is monotonic. And indeed, A union B is subset of A union B star because star makes things bigger. When we add C to both sides, the set inclusion still holds, and then we just apply star to both sides. And we obtain exactly what we were supposed to show. And now we have shown both sides of the inclusion, so we have shown, in fact, that our property holds. Function f, defined by when star is a closure operator, is in fact an associative function.